Okay, so I think we start. It's a pleasure to have Benny Sudakov as our speaker today. Thanks a lot, Benny, for agreeing to give this talk. And he will talk on three problems on three chromatic intersecting hypergraphs. If you have any questions during the talk, you can write in the chat, or also feel free to unmute yourself and ask it directly to Benny. He will not be following the chat because he will be next to the board. But if I see something in the chat, I will raise it to him, or you can just ask the question yourself. Yeah, thank you.
So thank you very much, everybody, for coming to this talk. So to cheer you up in how Gil in his blog tells in difficult times, I decided to do a board talk so that we will kind of feel some sense of normality. So I will give a talk about joint work with two absolutely fantastic young researchers, Matija Bukic and Stefan Glock, who are together with me in ETH Zürich. And I will talk about some really well-known problem, but maybe on the aspect of this problem which somehow lie dormant for 50 years, and I think it may be a good time to revive it. So let me start with a definition. I already pre-wrote various things, and then I slowly will fill the rest and give you new stuff. So I will say that a hypergraph has property B, which is equivalent to being two-colorable, if there is a subset of vertices X such that X intersect every edge, but is not contained in this edge, right? So this is the definition. Now you obviously see that this is equivalent to two-colorability, because if I have such set X, I can color it by red color, I can color the rest of the vertices by blue color, and therefore every edge will get red vertex, but would not be completely red, right? It will also have a non-red vertex, right? Because it does has vertices outside of sorry, not equal set E, right? So E intersection X is non-empty, but is not E itself, right? So therefore every edge has two colors. So the property B comes from named Bernstein, who in early 20th century studied this property for infinite hypergraph. And the interest to this problem was revived by Erdos and Hajnal, who in 60s asked the following question: what is the minimal number of edges we can have in K uniform non-two-colorable hypergraph edge? So let's denote this minimum by M of K, right? How small this hypergraph can be. So this is interesting also for its own right, but in addition, you can think about this problem from the point of view of colorability of hypergraphs. So we know that it's easy to check whether the graph is two-colorable. This is polynomial, but already checking whether the three-uniform hypergraph is two-colorable is NP complete. So because it's hard, you maybe want to know how the minimal non-two-colorable hypergraphs look like, and in particular, maybe you want to know, at least as a first question, how many edges they must have. So Erdos and Hajnal ask this question. And now it's very easy to determine the minimal number of edges in non-two-colorable hypergraph for small uniformities. So obviously, we know the answer for graphs, right? The minimal non-two-colorable graph is a triangle. We can also show that the minimal non-two-colorable 3 graph is a funnel plane. It has 7 edges. We also know that this function, for example, it's easy to show that it's at most exponential. For example, you can look on the complete K uniform hypergraph on 2K minus 1 vertices. So obviously, if you color it vertices in 2 colors, one color will have K vertices and would be an edge. So this guy is non-two-colorable, and it has at most 4 to the K edges. So it is a celebrated result by Erdos, which appears almost in every course on probabilistic combinatorics. There are actually 2 results. First, it shows that if you have a K uniform hypergraph with 2K minus 1 edges, then it's two-colorable. Actually, the random coloring will work in that case. And another interesting result of Erdos says that you can have a non-two-colorable K-uniform hypergraph whose order of magnitude is very close to the most constant K squared 2 to the K, and even that is proved using probabilistic method. So over the years, the problem of estimating MK attracted a lot of attention, and there were many very interesting approaches and tools developed for it. So currently, let me change this bound and tell you that the best bound we have for this problem is due to Srinivasan and Radhakrishnan, and its improvement of this lower bound roughly by a factor of constant K over O. So as I said, there were many interesting tools developed for this problem, and one of these tools I sure all of you know is a local lemma. So the local lemma was developed by in the paper by Lovasz and Erdos in 1973, exactly to study non-two-colorable hypergraphs. And this is the paper I'm going to talk about. So in particular, in this paper, Erdos and Lovasz, right, so as I said, it's 73, ask the following question. Suppose in addition of being non-two-colorable, we require our hypergraph to be intersecting. So by intersecting, I mean any pair of edges have a vertex and comma. What can we say about the properties of such hypergraph? Right? Is this clear? So this is the question which I addressed today. So you have K uniform, so my hypergraph would be always K uniform. The hypergraph is non-two-colorable, you cannot color it in two colors. And moreover, it's intersecting. What can we say about the properties of this hypergraph? And I'll be more specific. First, let me start by saying that obviously there are such creatures. So for example, the funnel plane, right? This three uniform hypergraph on 7 vertices, which I draw, right? Every 3 vertices here, which on the line, including this squiggly one, form an edge. Or the complete hypergraph on 2K minus 1 vertices, K uniform hypergraph, is definitely also intersecting. So we have such creatures. And once we have them, the first question which Erdos and Lovasz ask, how small such hypergraph can be. So again, now I want to know how many edges I must have in intersecting non-two-colorable K graph. So again, remember H for me in the stock always would be a K graph. So the first theorem which I proved in this direction, so this is a theorem of Erdos and Lovasz in the paper in 73, shows that this function m of k and squiggly of k is at most 7 to the power k over 2. So it's obviously at least m of k, so it's obviously at least exponential, right? We know that because it's non-two-colorable, and we need most 7 to the power k over 2. And the example, I'll write it here. I call it, maybe let me write it in red so you draw your attention. I call it iterated funnel plane. So what Erdos and Lovasz observed, that there is a very natural way to multiply, to take a product of hypergraphs, such that it maintains the property of being non-two-colorable. And through multiplying funnel plane with itself, they constructed a hypergraph which has roughly, which has uniformity k and roughly 7 to the power k over 2 edges. Now observe that this function, right, it's a square root 7 versus 2, it's way bigger than this function, which brings us already to the first super intriguing question, right? And so let me write this question. Question of Erdos and Lovasz. Show that this maximal number of edges in intersecting non-two-colorable hypergraph is also of the order of magnitude 2 to the power 1 plus little of 1. So this is the first open question which I want to mention. Right? This is a question which I don't I don't have anything new to say. It's really old from 73 and it's still widely open. And the main difficulty is, if people know the Erdos construction, is that the Erdos construction is indeed probabilistic, and it's very difficult to come up with a very natural distribution with a natural probabilistic algorithm which produces on one side non-two-colorable K-graph and on the other side keep its intersecting. Okay. Actually, this construction of iterated funnel plane is completely expensive. This is the first question I want to mention. Right? So the title suggests there would be 3 of them. So the next one is actually the next 2. It's about intersection spectrum. So let me give you a definition. So by intersection spectrum of the hypergraph, I denote it E of H. I mean the sizes of all pairwise intersection of Z. So I look on E intersection prime. I record how big it is for all E not equal to E prime belonging to H. So the spectrum is just what intersection sizes, pairwise intersection sizes I see. Now remember that there is a folklore result which says that H is not two colorable, then there is a pair of edges E and E prime such that the intersection is size 1. So if your hypergraph is non-two colorable, you have to have a pair of edges whose intersection is of size 1, otherwise the greedy coloring will work. Right? You color the vertices red as long as you can do this, and if you cannot do this, you color it blue, and this will work. So an interesting remark which was observed by Erdos and Lovasz says, right, so we guarantee to have in the spectrum the number 1. Now, if our hypergraph is non-intersecting, means there are 2 edges which do not intersect, we guarantee also to have in the spectrum number 0. And what they observe is that this can be the whole spectrum, right? So they exist non-two colorable H such that spectrum of H contains just these 2 numbers. So either 0, 1. And here is an example. So let me give you the example. The vertices of H would be all K-1 subsets of some universe. And the edges of H would be all K-1 uniform K-cliques. So you take on this set of vertices all cliques of size K. And now, obviously, the intersection spectrum of this hypergraph. So any 2 cliques, they can share only at most 1 common set of size K-1. So the intersection in this hypergraph is either 1 or 0. And this hypergraph, if your N is sufficiently large, is non-two colorable by Ramsey theorem, right? Because if you color all K-1 subsets of big universe red and blue, you will always have a monochromatic K. So the first interesting observation, which was proved by Erdos and Lovasz, and independently by Shelah, is that if you consider an intersecting hypergraph, something interesting happens there. You will always have 2 edges with a large intersection, right? So they claim that every non-two colorable intersecting H has E not equal to E prime such that the intersection size is of order at least k over log k. Right? And all my logs in this talk would be, say, base 2. Okay? So this is already interesting. So you will always have in intersecting non-two-colorable hypergraph two edges with a large intersection. So let me sketch you the proof of this, because this idea will be useful for me also later. So here is a proof. And so I prove by induction that there exists a set X of size, let's say R, hypergraph H prime subset of subhypergraph of H, whose size H prime has at least number of edges in H. Right? When I put here this vertical lines, I mean the size of H prime, number of edges, not the number of vertices. So it's size of H divided by k to the R, such that every f in H prime contains this set of X. So basically you started with intersecting hypergraph, then you can obtain slightly smaller 2 intersecting hypergraph, 3 intersecting hypergraph, and observe that unless your R is k over log k, then you obtain a subgraph of your hypergraph whose pairwise intersection is at least as big as that. Right? This is clear. So if you get this statement by substituting R k over log k. And why this is true? So we can do it by induction. Imagine I already have such H prime and the set X, right? I know that there exists edge E of H such that E intersection X is empty, right? So this is because my hypergraph has property B, right? So if my R is smaller, so maybe let me say smaller than K, if my R is smaller than K, then it cannot hit all the edges, because otherwise my hypergraph would be too colorable, if you want, or will have property B. And therefore there is an edge E which does not intersect this guy. But E intersect all other edges of H prime, right? E intersect all the edges of H prime because your hypergraph was intersecting. So therefore, right, for every F in H prime, E intersection F is not empty. So this will imply there exists a vertex V in E which is in 1 over k fraction of edges of H prime, right? Because since all edges of H prime intersect this E, at least one vertex, this E was of size k, would be in 1 over k fraction of F in H prime. So what we can do, we'll take mu set X prime to be X union this V, and we'll take H double prime to be all F in H prime such that F contains X prime. Right? And obviously, because it's a fraction 1 over k, we have that the size of H double prime is at least 1 over k is the size of H prime, which is at least the size of H divided by k to the power r plus 1. And this completes it. Right? So this is a very simple pigeonhole principle, which allows you, if you already have a set of size R containing all edges of some subhypergraph, increase this subset by 1. And again, if your R is smaller than k over log k, then obviously there is a pair of edges which have this, at least this intersection, and this process result. Okay? So actually, this brings us to our second question, which was asked by Erdos and Lovasz, right? The conjecture, let me put it, right? Conjecture. Erdos and Lovasz actually appears in quite a number of places. All the three conjectures appear frequently from 73. So Erdos mentioned it several times. It also appears in the book of Feng Chang and Ron Graham, Erdos and graph. So what they conjecture is that actually you can do much better than that. Right? The conjecture is that the maximum of the maximum intersection which you will have in the spectrum of non-two-colorable intersecting H should be of size k minus a constant. So this is a conjecture. So instead of k over log k, you can actually do better. You should get k minus a constant. And again, the best example which we have here, the smallest example which we have has intersection, the maximum intersection k minus 2, and it's an again iterated funnel plane, right? For many things which I'm telling you, this iterated funnel plane is kind of the best example which we know, and it has maximum intersection k minus 2. Okay. So now, so this is the second conjecture. So now let's come to the third conjecture. So here is the next question which Erdos and Lovasz asked, which is very natural question. So we know that if you take, again, non-two-colorable intersecting k-graph, we know for sure you should have intersection 1, because it's non-two-colorable. Now I showed you that it should have at least one very large intersection. But maybe, again, exactly as in the case of usual non-two-colorable hypergraph, it can have only two intersections, this one and this big one. Right? So they ask, can it be that the spectrum only has two elements? Again, the spectrum of non-two-colorable k intersect k graph, which is intersecting, right? It always would be the same object. Okay. And what they showed, and this was actually, it's a theorem because the proof is completely not obvious. They used in a very clever way the result of desert and sunflowers. They showed that the answer is no. That again, intersecting hypergraphs have a little bit different behavior compared to the usual hypergraphs. So they showed that every non-two-colorable intersecting k-graph, k-uniform hypergraph, has spectrum of size at least 3. So they managed to show that if you have non-two-colorable intersecting hypergraph, you always have at least 3 intersections. And again, what they did, they look on a natural example which they had, which is iterated funnel plane. And this iterated funnel plane, you can show right from the construction that the intersections there between the edges, they all have odd size, right? So example, this what is I call iterated. It has spectrum of size k over 2, right? And there is a huge gap, right, obviously, between 3 and k over 2. So they conjecture that the size of the spectrum, right, for non-two-colorable intersecting k-uniform hypergraph should tend to infinity together with k. This was the third conjecture. And today I want to present you a solution of this conjecture. Actually, together with Mattia and Stefan, we managed to prove this conjecture in the following strong form. We showed that every non-two-colorable intersecting K uniform H has its spectrum of size at least roughly square root of K. So we definitely managed to go way away from three intersection, but if you want, I mean, even the third problem is kind of still widely open because you really want to decide between this number and the example, or maybe you want to improve the example, or maybe you want to improve our proof. Okay? Now that's what we managed to prove, that every such hypergraph should have at least roughly square root K different intersections. Okay? And that's what I want to show you, or at least sketch you. I will be able to show you all the ideas. For simplicity, instead of square root K, I will roughly show you K to the power 1/3, but it would be already enough to show you all the tricks we're using to prove this result. Okay, so before start doing the proofs or giving you ideas, maybe it's a good time to stop and ask if there are any questions about what I just said. Okay. So if not, then maybe let me delete everything and just have a kind of free space so that I can really plan the proof. Right, so again, so you remember theorem, I want to show you the intersection spectrum. Right. This is what I proved, but we know, right, we know really 1/2 minus little 1, but that's a little bit more to show, a little bit more work to show.
Maybe it's a bit too small, right?
Okay, right, I will just, it's a reminder for people, I gave you a right big, so no voice. So, so the proof goes by using a combination of Ramsey type arguments with density increment. So in order to do density increment, let me give you a definition. Okay, so we have now our hypergraph H, right? So this is H, non-two-colorable intersecting K uniform hypergraph. We have two subsets of edges, S and T. And then we define the following things. So first of all, lambda S would be 1 over S choose 2 sum E intersection E prime, where E prime means. Right? So basically what you do, you go over all pairs of edges in S, take the intersection and average over all the pairs. And similarly, I will define lambda ST for two families of edges. It would be again average 1 over size of S times size of T. Right? And again, it's a sum over E intersection F, where E is in S and F is in T. So just lambda S, it's an average intersection of edges in A, S, and lambda ST in its average intersection of pair of edges across. Is this clear? So this is an important definition. And to illustrate its importance, let me give you a proposition and a corollary, which would be important for me. So imagine you have S and T K graphs, right? And they both have the same number of edges, L. Right? So you take two collection of edges, both having L edges. Then what we can show is that if you take all intersection of guys across inside S, plus all intersection of guys inside T. So this is at least as big as all intersection across with a small correction, right? Unfortunately, we will have to have this tiny error term, which would be easy to deal later, but it causes some trouble. I'll mention this. Right? So basically, the statement says that if you have two families, the average intersect, I will move to the average, but you look on the intersection inside the first family plus the intersection inside the second family, it should be bigger or equal that the kind of average intersection. So here is a proof. The proof is simple Cauchy-Schwarz. So for every x is a vertex, let Sx and Tx be the number of sets containing x in S and so I go over all edges in S. I see how many of them contain x. This would be Sx. I go over all edges in T. I see how many of them contain x. This would be Tx. And now I observe the following simple inequality that Sx choose 2 plus Tx choose 2 bigger or equal than Sx times Tx minus Sx plus Tx over 2, right? So what I wrote here is just true for any two numbers, Sx and Tx. But now, right, so this is always true. But now observe that when you add, right, so add over all x, then you observe that this side gives you this contribution, this thing gives you this contribution, this thing gives you this contribution, and Sx, sum of all Sx's is just sum of the sizes of the edges in S. It's L times K. Sum of the all Tx's is the number of edges in T times their size. Again, okay, so divided by 2, this is your error. So this is a pretty straightforward, right? So this is just true for any pair of numbers, but when you add this for all x, and you use the meaning that Sx was the number of times x appears a vertex among the edges in S, and T is the number of times x appear vertex among the edges of T, you get this side plus this side, and this is a vertex. Any questions? So here is an important corollary. This is what I'm going to use. It's not a very difficult corollary. As I said, I would be more interested in the averages. So you take this inequality and you divide it roughly by L squared. Actually, you divide it by L times L minus 1. And then you get here twice the average of the intersection in S plus twice the average of the intersection in T, bigger or equal. This is roughly, it actually works in your favor because here you need to divide by L squared. Intersection across plus K divided by L squared. So by L minus 1. So this is the first thing which you get is lambda S plus lambda T divided by 2 greater or equal lambda ST minus K over L minus 1. So this is the first very simple observation. You just divide everything by L times L minus 1. Another important thing, that this would be really very useful for us. So another observation we can do is we can greatly improve this inequality if we would know that there is some subset of vertices which is contained in every edge from S, but is not contained in any edges of T, right? So let's write it. If X vertices belong to every edge in S, and disjoin every edge. Imagine you found collection of vertices whose number is x, such that every edge in S contains this collection, and every edge in T disjoint from this collection. Then you can improve this inequality. You can write lambda S plus lambda T divided by T is greater or equal lambda ST plus x over 2 minus k. And so you have this additional x over 2 which you get. Again, the proof is pretty straightforward, right? You again use this inequality, but before you use this inequality, you delete this set of x vertices from your universe. So observe that since you're deleting it from every set in X and they all contain it, this part, the pairwise intersection, do not change. T was disjoint from X. So again, here didn't change anything. But when you take intersection across, in the intersection across, since F didn't change, you didn't change anything. In intersection for the edges in T, again, you didn't change anything because you're not deleting anything from them. But the intersection between edges from S, from each of them, you deleted the same set of vertices X. So therefore, this part dropped by X. And I just move it to the other side. So this decreased by X. So it means I can move it to the other side and get a positive increase by X. Okay? So this is a very basic observation. So if we have the situation where they all S's contain some set and all T's, all edges in T's are disjoint from this set, I can have something like a density increment. Now here is an idea how we do the proof. So let me give you for that a definition. So this is a definition of lambda I pair. And so what is a lambda I pair for me? So lambda I pair for me, it's a subset of edges of size, let's say for this talk it would be k to the 1/3, and another sub-hypergraph h prime of h, such that intersection of edges E intersection F all equal lambda I, where E comes from S and F comes from S union H prime, right? So lambda I pair would be some small set of edges, roughly of size k to the 1/3, and some hypergraph of my original hypergraph, which usually would be very big, such that pairwise intersection of every edge of S with itself and with any edge in H prime has the same intersection lambda. And so what would be my idea? So the idea would be the following. So first of all, I write you a simple Ramsey type statement saying that I always will have a very large such pair. Large by me, the H prime will contain many, many edges for some lambda I. And then the goal would be the following, and I'll show you how to achieve it, given lambda I pair, right, S and H prime, get lambda J pair, say S prime and H double prime, such that two things happen. First of all, lambda J would be strictly the lambda I. So you increase on average all pairwise intersections to the next possible intersection. And the second thing is that H double prime should be quite big compared to H prime. So you would say it should be size of H prime to the power K, roughly to the power K to the 2/3. And obviously, right, lambda J here, right, because right, it's lambda J pair, it's one of the intersection sizes, right? So you observe that My lambda I pair only defined when lambda is one of the intersection size. Okay? So this would be my goal. Now imagine if I can achieve it, then if I try to show you that the number of pairwise intersections is roughly k to the 1/3, if I always can move to the next lambda j pair by pairing roughly k to the power k to the 2/3, I definitely can do this k to the 1/3 times until I exhaust my hypergraph. And that would be the proof. So now let me tell you how I will do this. For this, one thing which I also still want to remind you before I give the final kind of steps of the proof is one can prove the following Ramsey type proposition. So again, we have a hypergraph H with possible intersection sizes, as I said, lambda 1, lambda 2 up to lambda t. I think always that I'm trying to show you that t is k to the power 1/3 minus epsilon. So that's what I'm trying to achieve. So these are all the intersections. So then I want, then this proposition says, then there exists a pair S and H prime such that right, so remember my t was k to the 1/3, such that the size of S would be of order k to the 1/3. Second, for every or maybe intersection of E intersection F equals lambda I, for every E in S and F in S union H prime. And the third thing is that H prime is pretty big. The number of edges I started with divided by k to the power equal of k to the 2/3 minus epsilon. So this is what I claim. You give me any hypergraph. Suppose there are only t possible intersection for pairs of its edges. Then I can find inside a subset of edges roughly of k to the 1/3, and another sub hypergraph which is pretty big, which is h, the size of the h divided by k to the power roughly k to the 2/3, such that all pairwise intersection between edges in S and edges in S or H prime have the same intersection lambda. So essentially I said that I can always find a lambda I pair for some lambda, right? For some I. This is really important. So far I don't have control of I in every such hypergraph. Right? And I can not only can do this, obviously I can apply this lemma not only to H, but I can also apply it to any sub-hypergraph of H. So this lemma shows me that I have at least an initial point, right? So, and the proof of this lemma is just Ramsey theorem for T colors. So basically what you can do, you can build an auxiliary graph whose vertices are the edges of your hypergraph, and two edges are connected by an auxiliary edge of color I if the intersection is lambda I. Now what you need to find in this coloring a monochromatic pair, some small set of vertices and huge set of vertices, such that all the edges between this small set of vertices and this huge set of vertices have the same color, and just the usual Ramsey proof, how we prove the bound on Ramsey numbers, give it to you. So I will not do it. Okay. So perfect, right? So now I have everything which I need to finish to give you the ideas of the proofs. So again, I start my argument by looking on my intersecting non-two-colorable hypergraph H. which has only k to the 1/3 minus epsilon intersection, and I want to get a contradiction. I want to show you that I can continue at least k to the power roughly 1/3 this procedure. I will start with some lambda I pair, which is pair like this, and every time I will move to a bigger lambda j pair, where lambda j bigger than lambda I, by decreasing the size of the underlying hypergraph, the number of edges, roughly by k to the power k to the 2/3, maybe minus epsilon. And since I can do this more than t times, I will get a contradiction, because in the end I will get a hypergraph which still needs to have an intersection, but it would be none of my numbers lambda 1 up to lambda. Okay? So I just need to explain you how to make this transition. Right? So again, setting. Right, so we have lambda I pair, SH prime, right, which again means S is of size k to the 1/3, and E intersection F equals lambda I for every E in S and F in S union H. Now, first thing to observe is the following. If this is my situation, then I know that for every subset R in H prime, I have, if I look on average intersection among the edges of R, they at least as big as lambda I, roughly lambda I. Say my R is big, R is of size also at least k to the 1/3. Why this is the case? So you remember this corollary about the averages of two sets. So if I take S, and then instead of T, I take this R. So I know that the averages of the lambdas, so lambda S was lambda I, and I know that the averages of these lambdas is at least lambda ST, which is again lambda I, minus k divided by L. My L was k to the 1/3, so this error term gives me k to the 2/3. So the first observation which I have, that if I have a lambda I pair, then I know that all intersection inside S, they lambda I, all intersection across they lambda I, but even on average, all intersection inside H prime, right, inside any big set, if I take the average intersection, it is very close to lambda I. It's not very small. It's lambda I minus a little. So now, we have two cases to look at. So we fix some H E inside S, and we look on all intersection of F with E, where F belongs to H prime. We have two cases here, right? So I look how all these edges in H prime intersect this fixed H E. E plays no role. So the first case, number 1, which I call concentrated case, says that for every F and F prime, F intersection E is very similar to F intersection E prime. And when I say very similar, I mean there's difference, they differ, right? Differ in roughly k to the 2/3 points. So if this is the case, then by pigeonhole principle, right? So basically I fix one F and I look on all F primes, right? And they contain almost the same set as F contains on E. So by just looking how many vertices I kind of need to delete, to make them equal. It's k to the 2/3. And there are only few subsets of size k to the 2/3 inside E. So you remember, E was of size k. So the number of such subsets is roughly k to the power k to the 2/3. I can get a subset X in E. My X is roughly of size lambda I. And I can get another hypergraph, H1 sub-hypergraph of H prime with the following two properties. X is subset of F for every F in H1. And this H1 has size roughly the size of H prime divided by k to the constant k to the 2/3. Again, why? Because, right, as I said, I fix one F, all other F primes intersecting roughly in this set, maybe with a correction of k to the 2/3 vertices. So the number of corrections which I have by picking holes is at most E choose k to the 2/3, it's at most least. So they would be the same correction repeated at least that many times, which means that it would be the same set X containing all these edge sets. Right? And now note that, so you remember, right, once I have this, so these guys now, not only their intersection is very close to lambda I, they more or less contain the same set, right? They contain the same X. So what I can do, I can use this trick, right? I can show you that there exists a set Y such that the set of Y has size the set of X plus R, right? So I already found you an intersecting hypergraph where all the intersections are of size at least X. Now I can go and I increase this intersection by one vertex at a time, R times, such that, and I can find a H2 subset of H1, such that H2 has at least H1 over k to the constant k to the 2/3 vertices, and every F and F prime in H2, they have intersection at least Y. So Y is contained. Right? So this is the usual. I actually can put here R just to be more precise, and then I take my R to be constant k to the 2/3. Right? So I can do this. It's exactly this argument which I gave you in the beginning. If I already have intersecting hypergraph, which is subgraph of the non-two-colorable hypergraph, I can increase the size of this intersection by 1 every time k fraction of 1 over k in the size of the hypergraph. So I do this R times. I choose my R to be k to the 2/3. And now observe that if this guy was close to lambda I, and I add k to the 2/3, I will get, right, that the size of the Y will be strictly bigger than lambda I, and therefore I move to the next intersection. Right? So this is the first kind of case. Now let me explain you the second case. The first case was where all the intersections of edges with E were roughly the same. So the case number 2 is if all these intersections are quite different. If for every F and F prime, F intersection E minus F prime intersection E, say bigger than k to the 2/6. Okay. So I look on the intersection, and they all behave very differently. Now observe what I can do. So since these two sets are different, I can find a set X such that X, say, would be 12. This constant is not important. K to the 2/6 vertices. And X is a containing F intersection E. And X is disjoint with F prime intersection E. So basically, for any pair of edges, I can find a big set which contains in the first and it's disjoint from the second. And again, I can do this for one pair, delete it, do the next pair, and every time I get set X. And observe that this X, right, since X is subset of E, and it has this size, there are at most k choose, I don't know, 12k to the 2/3 such X. So therefore, I can produce many pairs, right? H, F, and H, F prime, X is an F, X is not, it's disjoint of a prime, which have the same X, right? So basically, what I can do, I can find two hypergraphs, H1 and H2 in my H prime, and a set X of size 12k to the 2/3, such that every F in H1 contains X, every F prime in H2 is disjoint from the set X. And now note that both X1 and X2, their sizes are at least as big as my original H prime divided by k to the constant k to the 2/3. And now, to finish the proof, you know, what I can do is the following, right? I can use my lemma to find, right? Find S H1 prime lambda p pair in H1. So H1 is some hypergraph of my hypergraph. So I can find some lambda p pair inside it. I can find P, or maybe let's say S prime H2 prime lambda q pair in H2. So for each of these hypergraphs, I can find a pair inside them, such that all intersection here are lambda p, all intersection here lambda q. And to conclude the proof, I either have lambda p or lambda q bigger than lambda I, so that would be a good scenario for me, or if they both smaller, right? If they both lambda p and lambda q smaller or equal than lambda I, then observe what I can do. They cannot be really much smaller than lambda I, right? I know that they're at least as big as they're at least as big as lambda I minus 2k to the 2/3, right? So what I can do, I can take a new set up, which would be S union S prime. Right? And now what I know about this set, I would know that if I take lambda R, right, in this set, this lambda R would be consist of, right, so it consists of lambda S1, lambda S prime, and lambda S prime. And this lambda S prime, I know that it's really dropped down because observe that this was the thing which we wanted, right? For every guy in S and S prime, guys in S, they all contain the same set X. Guys in S prime, they all disjoint to the set X. So therefore, I know that lambda S prime, it's lambda S plus lambda S prime divided by T minus X over 2 plus K divided by K to the 1/3. And now observe that you're subtracting here. So X was 12K to the 2/3. So you're subtracting 6K to the 2/3. Right? And so this is at most lambda I. this is at most lambda I, but this drops really substantially. So you can show, I will just by averaging, that lambda R is at most lambda I minus 5/2 k to the 2/3. And observe that this would be a contradiction, right? We know that all the sets which we have, they should be at least as big as lambda I minus k to the 2/3, and I have here 5k to the 2/3. Oh, my time is over, so I'll stop here. Okay.
Thank you, Benny. I invite everyone to unmute themselves and give a round of applause to Benny, and then we can pass to Q&A. Okay, so feel free to ask questions.
Benny,
Yes.
you hear me?
Yeah.
Yeah, Joel here.
Yeah.
Thanks for a wonderful talk. And certainly this was a problem that Uncle Paul was very interested in for his entire lifetime. I did have every answer opens up new questions. Can you say more about the nature of I of H? Does it have small elements, other than one, of course? Does it have large elements? Does it have medium-sized elements?
So I mean, it's hard to tell. I mean, this proof shows you that, you know, you definitely, if it has, you know, lots of elements in which are small, you can produce many more intersections from them, because observe in the beginning, the stepping up is very, very easy. So I can step by steps roughly, I don't know, k to the 2/3, or if I want, I can change it to square root k. So if you tell me that your intersections are in the very beginning, then I can even increase, I can decrease my steps and therefore have many of them, right? So if you tell me, for example, that your intersections are all living in, so somehow, actually this pigeonhole principle, which I described in the beginning, shows you that your intersections, the small intersection, you can easily brush off by basically adding one vertex at a time at the expense of k. So until I reach intersections of size k over log k, I mean, I mean, the rightmost k over log k of them, but they're not so interesting. So the interesting thing happens with the large intersections, and unfortunately, those I don't know how to control. Right? All my intersections are pretty big, so the only thing which this argument shows is that how to kind of do a little bit of stepping, but this is a difficult case, right? Where if all intersections or many intersections are small, I can really get rid of them and go to the big intersection. But the big intersections are really stumbling block here, and I don't understand very well how they should behave. As I said, I mean, it's even a big open problem for me to see if I can get all the intersection, instead of being odd, maybe being divisible by 3 or being divisible by 20. Obviously, it's possible, right? If you find me another hypergraph, like a funnel plane, which has all intersection in certain kind of, with certain properties, I can take product of it with itself and get a new example. But somehow it seems hard. So I think the difficult thing here is to understand how the big intersection behave. Right? The small intersection, I mean, I also cannot tell you precisely what they are, obviously, but I think they may be less interesting. The more interesting here, what happens with the big intersection, just from the proof. Fortunately, yeah, it doesn't, I'm not answering your question so well. I don't have a good grip on the intersection, but I think if you want to understand the intersection, the first thing you want to understand is how big intersection behaves.
Okay, thank you.